You're watching a Channel 98 NBISD TV production.
Hey, welcome to That Geometry Show. I'm your host, Kevin Corpy, and I hope everybody out there had a great Thanksgiving week. If you were like me, you had a successful Thanksgiving by eating way too much. So I know all of us are looking to go a little bit light here. So keeping that in mind, I prepared kind of a light lesson today, kind of a low calorie but high in content, which is going to be very, very healthy. So let's go ahead and jump right in. Hope you have those sheets downloaded already from the district website. In case you've forgotten what that website is, it's www.newbraunfels.txed.net. Go ahead and download those, and we will jump right into Lesson 12. All right, Lesson 12 corresponds with the Glencoe Geometry textbook, Chapter 5.2, and we're going to jump over to 8.1 today. We're going to be looking at right triangles again and the Pythagorean Theorem again. So kind of a review of two previous episodes. By the end of this lesson, though, you should be able to determine if two right triangles are congruent, and you should be able to use the Pythagorean Theorem to solve problems. Okay? Now, a few episodes ago, we did look at determining whether any two particular triangles were congruent, and today we're going to kind of do the same thing for specifically right triangles. But to review, remember there were several combinations of sides and angles. Each triangle had three sides and three angles, and we only need to look at a certain combination of those to conclude that two triangles were congruent, which means all their angles and all their sides were the same measure. They were, in no particular order, the SSS, the side-side-side case. If three sides were congruent to three other sides, the triangles would be congruent. There was the SAS, or side-included angle, side-angle-side case, the angle-angle-side case, and the angle-side-angle case. So all we really need are three of any of those things in this combination to prove that the two triangles were congruent. Now today, again, we're going to look at a special case for right triangles, which we actually did on the previous show. Now, when we're going to be determining that if two right triangles are congruent, we always need to remember that we're given one of the angles. In a right triangle, by definition, one of the angles is 90 degrees, or a right angle. Okay, that's why we call it a right triangle. And though all the above methods work on right triangles, the side-side-side, side-angle-side, angle-angle-side, and angle-side-angle, they apply to right triangles. There is one special case that works only for the right triangles. Only for the right triangles and not for the others. And if you recall, it's called the HL case. And I'll tell you what HL means here in just a second. Here's what it says. If the hypotenuse, H, and the leg, L, of a right triangle are congruent to the corresponding parts of another right triangle, then we can say the triangles are congruent. So let's look at these triangles right here. This right here would be the right angle, and this right here would be the right angle. And remember, we denote the right angle with that little box. Okay, so this says that if the hypotenuse, remember the hypotenuse is always opposite the right angle, so if these two triangles had hypotenuses, which were congruent, and we also knew that one of the legs was congruent. So let's pick a leg here. This one, we'll put a double tick mark, and this one a double tick mark. If I know then that these two hypotenuses and these two legs are congruent, then by the HL, or hypotenuse leg case, I can assume that these two triangles are congruent. Now, what we really have here, if this wasn't a right triangle, is we have a side, and then going around the triangle we have a side, and then going around again we have an angle. So remember, that was the side-side angle case, or the ambiguous case. And that did not work in general for triangles that were not right triangles. But it does, however, work for right triangles. So you have to be careful when using the side-side angle case. If it's a right triangle, it works. If it's not a right triangle, then they won't work. Okay? Here's an example. Determine the reason that triangle NKL and triangle NJL are congruent. And then once we do that, we can find the measure of angle J, if we know one of the angle measures. Okay, let's set out first to show or find out why these two triangles are congruent. The first step is to clearly identify them. Triangle NKL. So here's N, there's K, there's L. So that's one right triangle. And triangle NJL would be this one, NJL. Now notice that they do share one side in common. These red tick marks here mean that this, which is a right angle, right here, so this is the side opposite, this is the hypotenuse, this is a right angle, so this is the hypotenuse. So we know that in these two right triangles, the hypotenuses are congruent, and since they share the same leg, basically, that has to be congruent to itself. So I guess you can put a double tick mark there, and that would cross through both of them. So now, since we know the hypotenuse and a leg in a right triangle is congruent to the hypotenuse, the corresponding leg, and the corresponding angle in the right triangle, these two triangles are in fact congruent by the HL case, by the hypotenuse leg case. Okay, so now that we know that, let's answer the next part of the question. Find the measure of angle J. Here's angle J down here. I want to know what that is. If the measure of angle KLN is 20. So if this angle right here is 20 degrees, we need to find this angle over here. Wow, that's pretty far away. Well, let's think about it for a second here. If I look at the entire big triangle, okay, this one here, it is an isosceles triangle because these two sides would be congruent. So I know that the base angles here would be the same measure. Now, because this right here passes from a vertex to the opposite side in an isosceles triangle, and it's perpendicular, this is a median and a perpendicular bisector and an angle bisector, which is important because now we know that if this angle is 20, this other angle here, angle JLN, has to also be 20 degrees. And now it's pretty easy to figure out what angle the measure of angle J is, because the sum of all the angles in a triangle have to add up to 180. Well, if this angle here is 90 degrees, that leaves only 90 degrees left over for these other two angles. So if this one's 20, this one has to be the complement, which would be 70 degrees. Okay? Because 70 plus 20 is 90. Okay? Pretty easy there. All right. Find the value of x so that two right triangles, triangle ABC and triangle XYZ, are congruent by the HL postulate. Okay? Assume that angle B is the right angle. Well, do you see any triangles drawn? Yeah, I don't either. Okay? So our first step is to draw two triangles that we can reference. I'm going to draw them up here. Now, they're right triangles, so I typically like to draw a right triangle in a very convenient format. I make the base angle flat, and I make this angle here the right angle. Okay? So find the value of x so that the two right triangles ABC and XYZ are congruent. So one of these is going to be ABC, one of them is XYZ. This right here is the most important piece of information. Assume angle B is the right angle. So if I call this triangle ABC, this would have to be vertex B. And then the other two are A and C. And it doesn't matter how I order them. I'll call this one A, that way this one's B, and so this one's C. Now, how are we going to know which one to call the right angle on the other triangle? Well, remember that if two triangles are congruent, the way in which we write the letters has to correspond to the congruent parts. So if angle B was the right angle in triangle ABC, then the corresponding position, the second place in the other triangle, in this case angle Y, would have to be the right triangle. So I'm going to label this one as Y, and then I label the top A, so I'm going to have to label the top in the corresponding place X. So I got X, Y, Z, and A, B, C. So setting up your diagrams and labeling everything is really the first critical important step. Now that I know that, I can actually look at the information and label what I have. It says that segment AC is 28. So that's going to be this here. That's the hypotenuse. And AB is 7x plus 4. So that's this segment here, 7x plus 4. ZX is the other hypotenuse right here, and it's 9x plus 1. And then I have YX right here being 5 times x plus 2. 5 times x plus 2. Now, because I know that these two have to be congruent, I know that their corresponding parts have to all be the same measure. So I can look at the hypotenuse of one, 28, having to equal the hypotenuse of the other. So I can say 28, segment AC, has to equal the measure of segment XZ, which is 9x plus 1. And so now I have one equation with one unknown. If I subtract 1, I get 27 equals 9x. And dividing both sides by 9, I get x equals 3. Okay? And so that would be the answer. I've answered the question. So what was all that other information in the problem? Did I need it all? Well, actually, no. I could have, though, however, said that segment AB, which is 7x plus 4, has to equal segment XY, which is 5 times x plus 2. I could have chosen to set it up that way. Now I still have one equation with one unknown. There's just two different places where that one unknown is. So there's a little bit more math involved. I'd have to distribute on this side, and then I have to collect my x's on the left. So 7 minus 5 is 2x. Bring my numbers to the other side. 10 minus 4 is 6, and then divide both sides by 2. I get the same answer, x equals 3, which is nice, okay? I should get the same answer. So in this case, we had a choice as to which method we wanted to use. All right, we're going to take a break now and watch some valuable public service announcements. But if you know what's best for you, you will not go anywhere. We'll be right back.
So, Sarah, what's going on here? Sarah? Sarah?
She won't answer you. Or she can't.
Why not?
This is the way it's been since she started smoking pot. She's all lazy and boring and... You know, we used to have so much fun together.
And now?
This is what we do.
Bad people, the gang members in the neighborhood. My brother, he wouldn't be happy at all if I was to tell him I was going to drop out of school. He would not approve of that, because then that's going to be two of us not handling our business.
Me and my friends are close, and we all believe in each other. I know they could graduate, even if it takes them longer than the 4 years.
We have classes together, so
we study together, we help each other with our homework.
Realized we messed up in the past.
Failed a couple classes before, not doing as much work as I should be doing. My two best friends, they keep me working hard.
Good to see you obeyed and you stayed put. We're going to get right back to that geometry show. Now on to the best part about right triangles, the Pythagorean Theorem. Really one of the most important theorems discovered in the ancient world. Many applications. Now we've already talked about this in a previous episode, lesson 2. Remember what the Pythagorean Theorem stated. It said the sum of the square of two legs of a right triangle equals the square of the hypotenuse. Well, that's a lot of verbiage here. The diagram will help us see what we're talking about. I have a right triangle. Here's the right angle. So remember the side opposite the right angle is always the hypotenuse. And then the two other sides are the legs. So out of convenience, we'll just call the hypotenuse side C and any one of the two legs A and B. It doesn't really matter. So the theorem then would state that A squared plus B squared has to equal the third side, the longest side, the hypotenuse, squared. A squared plus B squared equals C squared. Okay? Pretty easy to remember. Now, we're going to look at an example of using the Pythagorean Theorem. In this example, we want to find the value of x. Notice we have a triangle with a diagonal drawn from the top left corner to the bottom right, creating a right triangle right here, and another right triangle up here. Well, I have that this side length is 4, this side length is x, and the hypotenuse, since it's opposite the right angle, is 11. I need to find the value of x. So, carefully setting up the Pythagorean Theorem. I know the hypotenuse opposite the right angle always goes on its own side of the equation. So the other two legs, x squared plus 4 squared, has to equal 11 squared. And now I'll just expand. That's x squared plus 16 equals 11 squared, which is 121. So subtracting 16 from both sides, I get x squared equals 121 minus 16, which is 105. Now, coming up here, I will take the square root of both sides to solve for x, and I get plus or minus the square root of 105. Whenever you are introducing a square root to an equation, you should get in the habit of taking both the positive and negative square root, okay? Because there's all going to be two solutions. So now in this case, I want to interpret what is x? X is actually a length. It's a length of a triangle. So does having a negative length make sense? Well, not in my world, shouldn't in yours. So we just want, in this specific case, the positive root square root of 105, and so our answer is B. And the square root of 105 is not a perfect square, nor does it have any factors that are perfect square. So that's the answer. Okay, now there are certain combinations of three whole numbers that will always satisfy the Pythagorean Theorem. These sets of numbers are called Pythagorean triples. Okay? Now, if the measures of a right triangle are whole numbers, then those three measures, those whole number measures, form a Pythagorean triple. Now, I know you're asking yourself at home, what is a whole number? A whole number is basically in the set of numbers that we denote with this script letter W with a double bar. And it's basically the counting numbers, 1, 2, 3, 4, 5, 6, 7, with 0 thrown in. So 0, 1, 2, 3, 4, so on and so forth. Okay? Not the negative counting numbers, the positive ones, and 0. But no fractions, no decimals. So let's look at the example above. We had three numbers here, and we usually write them in increasing order. So our smallest side length was 4. The next largest side was the square root of 105, which is about 10 point something, 10.2 I think. So that would be the next largest. And if we get in the habit of listing our triples in increasing order, then the third side is always the largest, and it's always the hypotenuse. Okay? So is that a Pythagorean triple? Well, 4 is a whole number, 11 is a whole number, but the square root of 105 is approximately 10.247. Okay? And that is not a whole number. It's a decimal. Okay? So that would not be a Pythagorean triple, although it is a combination of three numbers that satisfy the equation. So Pythagorean triple, we're looking for nice, easy numbers, whole numbers. Okay, let's look at some examples of some numbers sets that are Pythagorean triples. The smallest such Pythagorean triple is 3, 4, and 5. Okay, they're sequential. We can verify that they're Pythagorean triples by plugging them into the Pythagorean theorem. And again, notice how they're in increasing order. Therefore, the last number is the hypotenuse. So I can say 3 squared plus 4 squared, does that equal? And I put a question mark on the equal sign, 5 squared. If it is a Pythagorean triple, then this statement should be true. So now evaluating, I get 9 plus 16. Does that equal 5 squared, which is 25? Well, adding 9 to 16, you do get 25 equals 25. So I'll put a check mark. Hooray! It is a Pythagorean triple. We just verified it. Okay? Another common one that you might come across is the triple 7, 24, and 25. Let's verify. 7 squared plus 24 squared equals 25 squared. Again, how did I know to put 25 all by itself on the right-hand side? It's the largest number, and because it was so, we listed it last. So now we'll just evaluate this side. 7 squared is 49. 24 squared is 576. Your calculator can help you with that one. And 25 squared is 625. Now adding them together, 49 plus 576 is in fact 625. And of course that equals 625. So check. I'll put my question mark back in here retroactively. This question mark on the equal sign kind of means that we're testing. And then at the end, when we do get a true statement, we can remove it and put a check mark. And if they weren't equal, we would put a not equal slash through. Here's some other examples where we're actually going to have to test. Which set of these numbers is a Pythagorean triple? If you get a question like this, there's a little bit of work to do. Okay? If you have your calculator, though, it makes the work a little more quickly. So here we go. We're going to have to set it up, and your teacher's going to want to see the setup for the test. So what we need to determine then is if 10 squared plus 15 squared, is that equal to 18 squared? So 10 squared is 100. 15 squared is 225. And what does that equal? That equals 325. Well, 18 squared is actually 324. Ooh, look how close they are. Does close count? Not really, not in this case. 324 is not equal to 325, so this is not a Pythagorean triple. How about 10, 20, 30? 10 squared plus 20 squared, does that equal 30 squared? Well, let's see. 10 squared is 100. 20 squared is 400, and we know that totals 500. 30 squared is 900. Ooh, yeah, not real close there. Okay, much further off than the other ones, but still not equal, so not a Pythagorean triple. So moving on down the list now, we got a 50-50 chance if we were to guess, but we don't have to guess because we know how to do these problems. So let's try this one out. 9 squared plus 40 squared. Does that equal the largest side, 41 squared? Well, 9 squared is 81, and 40 squared is 1,600. If you add those together, you get 1,681. So now we just need to check what 41 squared is. 41 squared, your calculator will help you with this again, is actually 1,681. and those are equal. So hooray, hooray, we found the Pythagorean triple. So we'll move on to the next problem. Nah. We want to practice, and we want to verify as well. So let's go ahead and try out choice D. If we got choice D being correct, then either the answer choices are wrong or we goofed somewhere. So let's check it quickly. 8 squared plus 10 squared, does that equal 12 squared? Well, 8 squared is 64, 10 squared is 100, and we know that totals 164. 12 squared, you don't pick up your calculator for this one. This is one you should know. That's 144, and these are not equal. So it's not a Pythagorean triple, and now with confidence, we know that choice C is the Pythagorean triple. Okay, returning to our diagram from earlier, we can use the same diagram to ask a different question. Okay, if triangle NKL, so that's this one here, NKL, is congruent to NJL, same as before, and NL right here, the common side is 8 feet, and KL, the hypotenuse of this one, is 10 feet. We want to find what JN is equal to. Oh, okay. Well, remember, we've already proven that these two triangles are congruent. Okay? So I know that triangle NKL is congruent to NJL. So finding the measure of NJ is going to be the same as finding the measure of NK because they're congruent. So I'm going to focus in on finding NK because I happen to know 2 of the 3 sides in that right triangle. So by the Pythagorean theorem, and again, carefully plugging in, here's your right angle, identify it. So opposite it is the hypotenuse, which I know to be 10. So that goes all by itself on the other side. So I know then that segment KN squared plus the other leg, 8 squared, has to equal the hypotenuse, which is 10 squared. And so I get the quantity Kn squared, and notice how I'm putting it in parentheses, plus 64 equals 100. Subtracting 64, I get segment Kn squared equals 100 minus 64, which is 36. Now we take the square root of both sides, and I'll show that here. Whatever we do to one side, we must do to the other. And so I just get segment Kn measures plus or minus the square root of 36, which is 6. So get in the habit of doing plus or minus, which will put you in the habit, hopefully, of then checking the reasonableness of your answer. We're looking for a length, so I don't want the negative. So I'm going to take the positive root, and since Kn is congruent to Nj, I now can answer the question and say that Nj, or Jn, remember it's the same, is equal to 6. And I probably shouldn't stop there, because you remember way back in the original problem, we actually had units. And so if there's units in the problem, you want to include units on your final answer, or you might lose a point. So the final answer is segment NJ is equal to 6 feet. Now it's time for the program that we call the Say What? Okay, and here's where the history comes in. Look at this little cartoon right here. You've got a Frank and Ernest cartoon by Bob Thaves. Here's what it says. Looks like Pythagoras out there is talking to his disciples. Okay, and what's he telling them about? He's telling about his discovery here, the right triangle. This was around 6th century BC. And they're chiming in after he's finished explaining it to them. Hey, you may be right, Pythagoras, but everyone's going to laugh if you call it a hypotenuse. Okay, and hypotenuse might seem like a pretty funny name, but there is a specific meaning to it. Hypotenuse comes from the common Greek root hypo, like in hypodermic needle, which means to go under, and the less common tine or ten, like our word tension, which means to stretch. So literally, hypotenuse means stretched under. And the reason we gave it that name is because the segment that is the hypotenuse was thought to have been stretched under the right angle. So if I draw a right angle up here, to go from this point here to this point here, I would have to span or stretch a segment across that distance underneath or opposite the right angle. So there you go, hypotenuse. Funny sounding, but very meaningful. Now here's an application that deals with computers or televisions. We got an actual computer here, not really actual, but a facsimile or a reproduction of a computer, and we're trying to find out what the measure of the diagonal is along the screen. And that's how TV monitors or computer monitors are typically measured. We know that this side is 19.5 inches long, and this side here, which is also this side, is 12 inches long, And we want to figure out what the length of the diagonal is to the nearest tenth of an inch. Okay? That's 1 decimal point. Well, this computer screen we can assume was built properly so that the corners are right angles. And since this is 12, this must be 12. So I can focus in on any one of these two because I know they're going to be the same. They're going to be congruent. So the hypotenuse, again, is opposite the right angle, so I'll set up my equation. 19.5 squared plus 12 squared has to equal c squared, my unknown. Now 19.5 squared is 380.25 with the help of a calculator, plus 144 has to equal c squared. We add those two together, and I'm going to flip the equation around. C squared is 524.25, and we'll take the square root of both sides, so we get c equals approximately 22.9 inches. We want the positive root. So a nice application of the Pythagorean Theorem. So there you go. Not a real big lesson today, but a lot of information there. A little bit of geometry, a little bit of algebra, a little bit of history, and even a little thing about computers. I hope you learned something today, and hope you had a lot of fun. Until next time, I'm Kevin Corpy, and I will catch you on the flip side.
You're watching